is there, that's good.
Yeah.
Otherwise, skip.
We are live now. We are live now.
Okay, fine. Excellent.
Okay.
It is perfectly done.
Please start.
So please check the YouTube. Is it live? So then you can make me as ACARR as host again.
Yeah. Just I returned my host, so just check it is properly done or not. Just a minute.
Yeah, we have made it from here.
I think you already host, right?
Yeah. So I will make you as co-host now.
Yeah, that will be better.
So I think we all are set. Time is 10 now.
Yes.
Yeah.
Dr. Shagata, live is already ongoing, right?
It is
Please
ongoing,
start.
sir. We tested.
Please start.
No. Okay. It is showing that it will start at 10:06.
We are already live and it's already time, so you can start. As a moderator.
It is loud. Yeah. So good morning to all. So we are gathered here for the lecture series on radar meteorology conducted by South Asian Meteorological Association in collaboration with Advanced Center for Atmospheric Radar Research, Cochin University of Science and Technology. So this meeting will be moderated by me. Along with me, one of my student, Miss Angel is here. So she will introduce a brief introduction about the course, please.
A very good morning to all. It gives me great pleasure to extend a warm welcome to each of you to the weekly online lecture series on radar meteorology. This series is jointly organized by the South Asian Meteorological Association and the Advanced Center for Atmospheric Radar Research, CUSAT, India. I extend my heartfelt greetings to all the distinguished guests, esteemed educators, and participants who have joined us here today. Without further delay, let us begin the program. Welcome address would be by Professor Someshwar Das, Secretary, SAMA. So I would like to invite Professor Someshwar Das to deliver the welcome speech. Dr. Someshwar Das is currently a professor of atmospheric science at the Central University of Rajasthan. Dr. Das has been actively involved in the severe thunderstorm observations and regional modeling program. His tireless efforts in severe thunderstorm research have led to the establishment of ACARR Storm Program, jointly undertaken by 8 South Asian countries under the South Asian Association for Regional Cooperation. He has published over 149 research papers in peer-reviewed journals, and he has received so many awards like SARC Award for Senior Scientist, Indian Society of Remote Sensing Award, etc. Please welcome Professor Das. Sir.
Okay, thank you very much, Angel. Namaste, good morning, everybody from India and Nepal. ABM Dr. Ajit Tyagi, President of SAMA. Chief guest, of course, Professor P.G. Shankaran. I hope that he should be able to join. As already told, he is traveling, he is in Pune. Vice Chancellor of Cochin University of Science and Technology. Guest of honor, Professor V. Chandrashekar, Distinguished Professor of Electrical and Computer Engineering Department, Colorado State University, USA. The special invitee, Professor K. Mohankumar, Founding Director of the Advanced Center for Atmospheric Radar Research, ACARR at CUSAT. Chairman of the advisory panel of the lecture series, Dr. Devendra Pradhan, is the former ADGM, Additional Director General of Meteorology of IMD. members of the organizing committee, distinguished participants from more than, I suppose, 35 countries. Ladies and gentlemen, I welcome you on behalf of the South Asian Meteorological Association, SAMA, and Advanced Center for Atmospheric Radar Research, ACARR, Cochin University of Science and Technology in India. This is a continuation of our efforts on capacity building of the people of South Asia and the member countries of the Non-Aligned Movement, NAM. Many of you may know that we conducted the first online lecture series on atmospheric physics jointly with the SRM Ministry of Science and Technology, Chennai, for 4 months during January to April 2023, in which more than 2,000 people from 48 countries registered for the course. We conducted the second online training on WRF modeling system jointly with the CDAC, which is the Center for Development of Advanced Computing in India, during 3 to 24 April 2023, with hands-on training on the supercomputing system of the CDAC. We conducted the third lecture series on satellite meteorology for 20 weeks during September 2023 to February 2024. This is our fourth attempt on capacity building of the people in radar meteorology. We have a distinguished panel of very senior scientists and professors from reputed institutions of this region who are experts in the field. The syllabus of the lecture series has been designed based on the feedback and requirements of the member countries of SAMA. This lecture series is targeted to
Sir, your screen share is off. You already screen share already off.
I'm not sharing my screen. Okay.
You are sharing your presentation?
No. I'm just.
Okay, sir. Continue, sir. Sorry.
Yeah. So, as I already said, this lecture series is targeted to postgraduate students and professionals of non-meteorological background who are interested in learning the subject of radar meteorology. This lecture series will continue for 5 months for 20 weeks from 25th May, that is today, until 2nd of November 2024. As already been announced, more than 1,000 candidates from 36 plus countries have already registered for the course. As of now, the number is still increasing. At the end of the course, certificates will be given to the participants who attend at least 75% of the lectures. Those interested in receiving certificates with grades like outstanding, excellent, very good, good, etc., will have to appear in a evaluation test by paying an examination fee. The amount of the fee and the mode of payment will be decided later. The lectures are live streamed on the YouTube channel of SAMA. They will also be available afterwards on the YouTube for those who could not attend the course live because of the time difference between different countries. We shall try to have more interactions between the speakers and the participants in this lecture series. Please write your questions in the chat box. Our moderators will pick up the questions at the end of the lecture and they will be answered by the speaker. So enjoy the lectures and I wish you all the best. Thank you very much. On to you, Dr. Ravilas. Over from my side.
Thank you very much, sir. Now, please introduce Tyagi, sir.
Now, for the presidential address, I would like to invite AVM retired Professor Ajit Tyagi, President of SAMA. Dr. Tyagi is also the President of India Meteorological Society and a Senior Advisor at Integrated Research Action for Development, New Delhi. He has served as Assistant Chief of Air Staff and Director General of Meteorology. He was instrumental in introducing numerical weather prediction and modernizing aviation meteorological services in the Indian Air Force. Dr. Tyagi has been associated with several field programs, including STORM, BOBTEX, and CTZZ. He has served on various committees of MOES, ISRO, DST, MOEF, NDMA, etc. He was awarded the Vishishta Seva Medal by the President of India for his distinguished services and leadership. Over to you, sir.
Thank you, Angel, and very good morning. I join Professor Someshwar Das in extending heartiest welcome to our esteemed guests. To start with, let me acknowledge the consent of the Cochin University for being a joint collaborator and active involvement of the director of ACARR, Dr. Abhilash, in hosting this important online lecture series, which was, I think, felt the need for which was felt for quite some time. And now, to start with, let me welcome and thank Honorable Vice Chancellor of the Cochin University, Dr. Shankaran, our chief guest, also the guest of honor, Professor Chandrashekar from Colorado University, and Dr. Mohankumar, the founder director of ACARR, who has, all of them have played a great role in promoting radar meteorology in the country. I'm very happy that we were able to formulate this program under the leadership of Dr. Pradhan, who was the chair of the advising panel, and also the organizing committee who had coordinated this program. And we are able to bring this 20-week lecture series with the participation of all our eminent scientists from India, working in the India Med Department, IITM, and the academic institutions, and also the organizing committee. Okay. Now the course has been formulated to cater the need of right from the beginners by introducing the basics of the radar meteorology, starting with remote sensing and also the various products leading to the its application in the research. So it covers people who are really getting interested in the radar meteorologist to the young researchers, and the lectures have been so divided in 3 different modules. So I am really thankful to Dr. Pradhan and his team in the advisory panel to have formulated this program. And thanks to CUSAT doing a lot of sped work in getting coordination with eminent scientists and to deliver these lectures. So please make best use of it. This is one of the rare opportunities for the students in the South Asian countries and the named countries to benefit. Thank you so much. Make best use of it and all the best. Once again, I am thankful to Professor Chandrashekar and Dr. Mohankumar for gracing this inaugural session. I am personally, thankful to Chandrashekar, who had been all through. I had been, associated and from the IMED days. He had been extending support to the all IITM, IMED, and other institutions, academic institutions, and research students, and even to the individual scientists and researchers. So this is great support from him to India. And also Professor Mohankumar, who had been the founder director of the ACARR and had been working tirelessly to bring the center a reality, and handing it over to Dr. Abhilash, who is another young dynamic researcher, and so I'm very happy that this course is being inaugurated today in the presence of Professor Chandrashekar. Because of time gap, we had to reschedule it in the morning. Otherwise, we have lectures in the afternoon. So my request to all participants and students is that please make full use of it. As Professor Someshwar Das has said, that you have to interact. You are offered to interact with our speakers by question and answer sessions, which the moderator will make so your interactions possible. And also, even after that, I'll request all our resource persons to help the participants to clear the doubts. So once again, my thanks to the Dr. Abhilash and Professor Someshwar Das, who have tirelessly planned these program. Required a lot of coordination and a lot of preparations. the team of ACARR who are supporting this program for 5 months long period. Once again, on behalf of SAMA and ACARR, I welcome you and thank you for your participation and wish this program a great success. Thank you, Jai Hind.
Thank you, sir. Thank you very much for your kind words. Now, since our Vice Chancellor is out of station today in Pune for attending another important meeting at Pune University, so he won't be able to attend this function today. So, without delay, I request Angel to introduce our chairman of this radar meteorology course, advisory panel chairman of radar meteorology course, Dr. Devendra Pradhan sir.
I would like to invite Dr. Devendra Pradhan, Chairman of the Advisory Panel, former Additional Director General and Scientist G at the India Meteorological Department, Government of India, to address the gathering. Dr. Pradhan's career spans over 40 years with significant contributions to teaching and professional practice. He joined the IMD in 1990, has taken on various roles with increasing responsibility, successfully executing projects involving the lightning detection work, DWR, and automatic rain gauges for better prediction and management of severe weather events. Dr. Pradhan's work has profoundly impacted improving India's meteorological infrastructure, particularly in areas prone to severe weather and hydrological challenges. His dedication to the field is reflected in numerous publications and his active involvement in various meteorological projects and initiatives. Sir, please.
Dr. Pradhan, please. Yeah.
Good morning, everyone. And my warm greetings to all the delegates, eminent scientists, especially to President Professor Ajit Tyagi sir, the President Sama, Dr. Someshwar Das ji, Dr. Abhilash, Professor V. Chandrashekar, and all others who have joined here and contributed in this very important meeting. Not only the meeting, I should say that is the beginning of 5 months long duration training in the radar meteorology. This is a matter of happiness for every one of us that more than 1,000 candidates have registered here for the training here. And since this training is unique in the respect of understanding of the Doppler weather radar, single polarization, dual polarization, their applications in nowcasting, in understanding the different severe phenomena, and since it has been divided in the simple parts such as the basics of the radar meteorology, the discussion over the severe events which have already occurred in the past, their analysis, the practice session, the question answer session for everyday lecture, and followed by the most important thing is that there will be one, I should say, the practical exam as well as a theoretical exam for everyone who is attending the training session. So hope that by the contribution of all the eminent scientists, Professor V. Chandrashekar, the scientists from IMD, scientists from IITM and others, they will contribute different aspects in the radar meteorology, starting from the very basics that even a person who does not know the ABCD of the radar and the Doppler radar, he will be able to understand each and everything. So this course has been designed in such a way that everyone will be able to participate. And the most important is it will be interactive kind of the session, such that whoever is having any problem in understanding any of the parts, that they can note down and they can have the queries cleared without any difficulties. So with the untiring efforts of Professor Ajit Tyagi sir, Professor Someshwar Das ji, and all others, and especially my sincere thanks to Professor V. Chandrashekar, Professor Shankaran sir, the Vice Chancellor of this thing, CUSAT, Professor Mohankumar ji, and so many others, those who have contributed here and they have devoted themselves and spared the valuable time for this radar meteorology. I am thankful to all the members from scientists from IMD, IITM and others, those who are making this radar training a success in all the respects. So once again, I'll remain this thing here, what should I say? I want to convey my thanks to each and everyone here, those who is contributing in this radar meteorology training. So welcoming once again all the professors, scientists, meteorologists, environmentalists for understanding hailstorm, thunderstorm, tornado, cyclone, and many other things in the radar training here. So thanks everyone once again from my side. Thank you, sir.
Yeah. So now it is time for taking photograph. I think all panelists can make a copy of this so that we can share later. So I request all who have joined here to switch on their videos.
Dr. Swagataji and Pradhan sir, please. And Joyantipal and T2K Samson. Dr. T2 Samson sir, please. Could you please switch on your video?
It too also joined from USA. So
Swagataji, please.
Ajit Tyagi sir. Yeah.
Ready? Okay. With that, the photograph will not be fulfilled. Ready?
Yeah.
3, 2, 1. T2K Samsung sir, his video is still switched off.
Yeah, it's okay. We can go ahead with the video. I mean, photo.
So last one, please. Final one. Okay. Ready?
One more.
Chandrashekar sir, please. Yeah. Okay.
Very long.
Thank you. Thank you very much.
So, so now I request all others to switch off their videos so that we'll move on to the first session of this program. So I request Angel to others. So I request Fatima from University of Dhaka, Bangladesh, to introduce the speaker.
Thank you. Please allow me the share option.
Please make her co-host, otherwise she cannot.
So we have already made her. Okay.
Not yet.
Yeah, Fatima. Oh, okay. Yeah.
I hope it is visible.
Yeah, it
Yes,
is.
yes.
Yeah.
Thank you. I'm Fatima Akhtar, Chairperson, Department of Meteorology, University of Dhaka. I'm grateful having the opportunity to introduce our speaker, Dr. V. Chandrashekar. He is Professor of Electrical and Computer Engineering, University Distinguished Professor. Dr. Chandrashekar has made pioneering contributions in the area of polarimetric and observations of the atmosphere. Dr. Chandra has extensive experience in radar system design, radar network development, DSP design, as well as RF communication systems. He has contributed significantly to the areas weather radar and application to atmospheric sciences. He also conducts research on related topics, including image processing, neural network applications, and large-scale system simulation. He has organized and participated in large multi-agency national level experiments involving many radars, aircraft, and ground instrumentation. He is an avid experimentalist, conducting special experiments to collect in situ observation to verify the new techniques and technologies. He is currently a co-PI of the CSU CHILL radar facility. He is a co-PI and the Deputy Director in the NSF Engineering Research Center, CSA, Center for Collaborative Adaptive Sensing of the Atmosphere. He has been a PI and co-PI on several national level programs such as the Advanced Communication Technology Satellites at CSU DRAPA NGI program, the current NASA TRMM mission, and the future NASA GPM mission. He has also been the director of the undergraduate program at Colorado State University. He has served as a visiting professor at the National Research Council of Italy and as a distinguished visiting scientist in the NASA Goddard Space Flight Center. He did his bachelor degree from Indian Institute of Technology in Electrical Engineering, MS from Colorado State University, and also he did his PhD in 1986 from Colorado State University in Electrical Engineering. He has lots of achievement. And
you can skip all that. It's okay. You don't have to read everything.
We are very much delighted to have Dr. V. Chandrashekar in our lecture series of radar meteorology. Thank you.
Thank you. So I'm going to share my screen now. And I hope you can see my screen. Do you see that?
Yes, sir.
Yes.
So what I would like to do today is, first of all, thank you for inviting me for this great event. And there are a lot of people who have contributed a lot to Indian radar meteorology. They're all here. I've seen myself, the passion that Dr. Devendra Pradhan has shown, and then the passion I have personally seen, the passion Someshwar Das has shown to introduce radar data into a simulation. There are some stories, but I unfortunately cannot share them publicly. But I wanted to dedicate this talk to one person, and that is none other than Dr. Ajit Tyagi, because he's the first one who brought dual polarization radar to India. I remember coming to India many times, and then so many senior people, including regional directors, regional center directors, and saying dual polarization doesn't work in India. It's not good for Indian conditions and all that stuff. But Dr. Tyagi came from outside. And then I don't know what he did, but I think there was some Asian Games or something that was going on, Commonwealth Games or something. He saw that opportunity and he brought the first dual pole radar to India. That has been a huge turning point. So because of that, otherwise, we will all still be measuring single polarization measurements because so many people were saying dual polarization doesn't work in India. That was a very common theme those days. So let's give him a big hand virtually. And Dr. Tyagi, can you appear on the screen so that we can see you also? So is he here? I want to dedicate this talk to him. I guess he is not here.
He should be there somehow. But actually,
Anyway.
he's in Trivandrum. He's probably traveling and joining remotely from Trivandrum.
Oh, there he is.
Thank you, Dr. Chandrashekar, for your kind words. See, this is what your guidance had been so encouraging, not only for the IMD, but for entire radar community in the country. And many of the younger people must be owing to your guidance and support. And your continuous support to the annual events which take place in India also is really very, very heartening, because that is the platform which provides young researchers to present their work. Thank you so much for agreeing to deliver this our inaugural address also, and we continue to look forward for your support. Thank you so much, Dr. Chandrashekar.
Thank you. So with this, let me get started. So I wanted
Chandra,
to.
can you just use the slide, full slide, so just to slide, so yes.
So I wanted to think of. I wanted all to think of not radar as an instrument, but part of infrastructure of the country. What is infrastructure? Infrastructure is like roads, airports, and satellites. So weather radars should be thought of as infrastructure, not as some instrument you buy and put it on the side. When you think of it as infrastructure, then it will meld with everything we're doing. So why do we need radars? We have satellites. A lot of people say, I have satellites. Satellite can do everything. I have rain gauge. I don't need radars too. There is this thing called global water cycle. So said in 30 seconds, water evaporates from the surface, becomes clouds, and then it rains, and then it runs through rivers, and then it comes back, and then goes through plants, evaporates, so on. But the water is continuously cycling. And we even have, and the water doesn't go out of the earth. The water doesn't go anywhere. It's like evaporating, coming back. It's like this old Sanskrit shloka, akasat patitam toyam yatha gacchati sagaram. So everything is a cycle, and the cycle has got a time constant. If you had a way of following this one particle of water, that time constant, it has been observed scientifically, is accelerating. What it means is the same amount of water is cycling, but it's cycling faster, which means 100-year floods are happening every 10 years, and more frequent and more extreme events are happening. It's hardly like we have to go to many 100 years in history of IMD to look at cyclonic storms in the month of May. So, and there is a cyclone in the Bay of Bengal now, right? That's what I was watching news. Anyway, let's keep going. What it means is we need to observe this more carefully. If you have a lot of mosquitoes, you don't run away from the city, you buy a mosquito net and start living. So like that, we need to build infrastructure to monitor ourselves. But also there is one more thing that's happening, why we need the infrastructure. In the year 2018 was like a tipping point. More than half the world's population is living in urban regions. By 2030, this number will swell to almost 5 billion, with most of the urban growth in Africa and Asia, which means there are a lot of people in a small space area. So we need to observe these things more frequently and more carefully, which means if the population increases, we need more radar, more roads, and more houses. It also means we need more radars that observe locally. So that's the big picture, why we need this. And this is, let's skip all this. There are a lot of studies in UN that have keep on doing this. That's because of never-ending migration. And you can see over the Indian subcontinent and then Southeast Asia, it's all filled with yellow and square dots. So any given time, it doesn't matter where you are, whether you're rich or poor, tall or short, there is flooding everywhere. Flooding in Mumbai, flooding in Louisiana, and flooding in Beijing. Doesn't matter how powerful you are, how rich you are. So urban flooding will be a major challenge with significant economic impact, which means we need to build infrastructure to manage this. What is the current vision strategy for radars? Radars are part of national weather and climate observation infrastructure to support forecast and warning operations, as well as aviation safety, flood mitigation systems, energy management, and smart city infrastructure. Take, for example, let me skip this. So another thing that about radars, as opposed to things like rain gauges or satellites that do passive measurements, is radars look inside the storm. They are like X-rays. They will tell you what's happening. I've written a new book that has just come out a few months ago. Each chapter tells what's the story with the radar. There is precipitation physics, that's in chapter 3, scattering, that's in chapter 4, network, chapter 10. So these are all looked at in different things. So what's happening in the US? So there are 160 WSR 88D operational radar systems. The 88D stands for 88 is the year it was deployed. And they look at 200 plus kilometers of reflectivity. And this is the national distribution of radars. Somebody put some big circles around it at 230 kilometers and declared the whole US is covered. And also today's weather radar networks are what is called as data push infrastructure. They go round and round and round. This antenna collects data and then pushes data to users. And then the users make decision making after processing the data. People like Someshwar Das will take it and put it into models. In the US, it goes into right now what is called as high resolution rapid refresh models, and et cetera, et cetera. And whereas the new systems, they will be what is called as data pull systems. Based on the needs of the local situation, the data will be pulled. That is, the radars in the Himalayas, right? Today, if you go, US National Weather Service, Florida and Seattle, the radars operate the same way. Similarly, in India, let's say Machilipatnam and Kashmir, radars operate the same way. There is no data pull process, and that will all change. And there will be a request, and then the service data will be provided depending on the prevailing situation. There is one more thing that's happening that's called the inconvenient truth. That is, the Earth is curved. So there is no point in designing radars for very, very large distances because electromagnetic waves travel in a straight line. So if you go very far, most of the low-level phenomena will be missed because of Earth's curvature. So we started a center to highlight this problem. Then we went and looked at the original study that was used to sell the NextRad program. I showed you, in fact, I'm going to go through. Look at this. This picture says the whole country is covered. But in this picture, look at the coverage, considering all the blockage due to mountains. And this is the coverage diagram at 10,000 feet. Nowadays, everybody flies. When I left India, hardly anybody flew. And when you are about to land, suddenly there will be a ting sound. And then immediately the pilot will come and say, straighten your seat, wear your seat belt, sit straight and everything. That's when the aircraft crosses 10,000 feet. It's an aviation thing. So this whole study was done from aviation perspective. Whereas you look at 10,000 feet, there's not many people who live at 10,000 feet unless you are in Dehradun, or well, Dehradun is also not 10,000 feet. But you look at coverage at 3,000 feet, this is the coverage over US. You can say a lot of coverage, US is not covered. So we are not making measurements close to the ground, and which is the problem. And so when you don't make measurements close to the ground, there is a big gap in the measurements. So we come up with all sorts of fancy algorithms to take these measurements and push it down. Anyway, so we bring this local regional networks to fill this so-called gap. And somehow this small radars have gotten the name gap filling radars, because US has already gone and bought this 160 radars. So we have to work with them. So the only thing you can do is fill the gaps. Whereas other countries who don't have a radar infrastructure can look at the problem fundamentally up. There is one more thing. In the old days, the observations were at a higher resolution than models. That is, before the year 2000, computers were not that fast. And then model grid spacing was not that high, but conventional observations were at a broader resolution. But then what happened was, after 2000, the computers took off. And then the model grid spacing kept coming down. But then we're not making as many observations. And there are very few, like radars are located sparsely apart. What does it mean? The model is just making up stuff because it's not pinned down on measurements. So we need to catch up with models with the higher deployment of radars. So all these details were studied, and then I served on a lot of these national committees, and we wrote a lot of reports to the government saying what should be done. And that's all being implemented one by one all over the world. In fact, there are many places in the world that's being implemented much faster than even the US and so on. So I hope all these three reports, I'm part of the right income group. So we make measurements when and where the user's needs are the greatest. And so the thing is, radars are an observing system, and they observe the prevailing weather, which is a physical system. So a physical system like atmospheric phenomena is described by law of physics, whereas radar systems are designed by rules of engineering. So the engineering system interacts with the physical system, and then we make forecasts and warnings and so on. But where does this combined system sit? This combined system sits with a system of people, which is forecasters, emergency warning people, and telling people to vacate. And, you know, in my own family, when there is a cyclone warning and there is flooding, and then my own parents refuse to vacate. That's the people system. What can you do with them? So we have to make a big system and involving people that communicate, that elicits the best response from people. Sometimes the response is obtained by force. Sometimes its response is obtained by strong advice. And so this is a combination of a system of physics, engineering sitting inside a human system. Okay, because sometimes, anyway, I don't want to digress in my topic here. Let's get to fundamentals, how this all happened. Let me skip all this details, and bottom line is you have to observe. Look at these years. It's 1984. I went to the US in 1981, and then there was a whole situation where we started designing this. We had to design new system of radars, because at that time, in the 80s, it was dominated by what is called the Cold War. And then there was a lot of a race to build better radars. And I was very fortunate. I didn't know what I was doing. I was just fortunate. And then I went there. I studied at IIT Kharagpur and I happened to, be at the radar center. And I learned all the radar education and then went there. So, and then 81 to 84, 3 years. And then this is the first picture of a dual polarization radar. This is the time I think Dr. Pradhan must have been in college. And I'm not sure what Dr. Tyagi was doing in 1984. Someshwar was a young man. So I don't know what he was doing in 84. And many of the audience, sorry?
I was doing PhD in IIT Delhi at the time.
Great. And many people in the audience are not born in that time. So this, I'll just tell you simple. This is before the days of color display. The whole state of Colorado had one color monitor, 84. It's very old. So this is a picture of in Colorado vertical section. And then this is the picture of dual polarization radar. This is direct picture from the radar. No image processing, no computing, no smoothing, no fake picture, no fake news, none of that stuff. Those days, what you see is what you get. And this is reflectivity. This is differential reflectivity. And you can see at the height of 1.5 kilometers, this changes from cold colors to warm colors, which is basically the transition from ice to water. A picture is worth 1,000 words, and also the picture gives information in your face. This was like you are digging in the ground and then you struck gold. Then it was so good, but people didn't believe that. I don't know. This is some strange phenomena that happens only in Colorado. It won't work in other places, people thought. So see this, 84. Then they gave us tons of money. This is 80s. There was a lot of research money those days. They gave us tons of money, said, go show this really happens in some very stormy place. So, you can't just take a radar and move in those days. It takes time. And this is 1986. And we went to and look at how tall the storm is, 16 kilometers or 17 kilometers. And I will come to the height of these storms. So here the melting layer is around 4.5, 5 kilometers. And you could see the same story here, that transition from water to ice. And this is a very tall storm in Huntsville, Alabama. If you go look at the news, these types of storms have happened over last months in US. So this dual polarization phenomena to observe physics was great. And then we never looked back. And then this is 86. But even then, it is too quick to turn it into operations. 1988, when the weather radars were introduced, they were still single polarization. It took till the year 2010 to convert the whole country into dual polarization. But anyway, so that's the infrastructure. So infrastructure change happened. Point by point, people went to the field and then change it to dual polarization. And I'm going to skip this and not drift into physics because then I will get too bogged down. Essentially, what is happening is the radars transmit at 2 different polarizations and then look at the dual polarization observations and convert into meteorologically useful quantities. And you transmit horizontal, receive horizontal, and then transmit vertical and receive vertical. That basically gives you dual polarization measurements. Looking back, it's all very simple. And then I will get to this. What do these radars look at? They look at a radar volume that's filled with raindrops or ice particles. So there's a lot of mathematics into it. I have written a whole book on this, but a lot of the raindrops have what is called as a exponential distribution. Gamma distribution is a special form of exponential. Basically, there is a large number of small drops and very few large drops. So you can see these are 2 different volumes, 1 meter cube. Here it's filled with 1 millimeter drops, and here very few drops are filled with 2 millimeter drops. Both volumes have a reflectivity of 37 dBz, which means probably 0.2 millimeters per hour or 0.3 millimeters per hour rainfall, generally looking. Otherwise, if you use a straight ZR equation, in this case, if it's filled with small drops, if it gets this reflectivity, it actually has 35 millimeters per hour. And here it is 6 millimeters per hour if it's all filled with 2 millimeter drops, but they have same reflectivity. That shows that reflectivity alone cannot do the job. You need additional measurements to solve the problem. And that's what dual polarization did. But while dual polarization was chasing this problem, it has solved many, many, many more things other than this. The main reason is the shape of raindrops. Raindrop shape is spheroidal. They're all like the shape of idli, but very small ones. Nowadays they make what is this thing called? Some tiffin idli or something? Some very, very small idlis. And so raindrops are of that shape. That is, you look from the top, it's a circle. You look from the side, it's an ellipse. So when radars described this phenomena, see, this is 1988. We needed to understand why that differential polarization is positive in rain region and zero. So I got into a plane and flew through a lot of, in 1988, I was very young. I flew into a lot of storms and took pictures of raindrops. See, these are all the pictures of raindrops I took. And then those days you make measurements and then it takes till many, many more years to publish. And I'm an engineer, but this is one of my most widely referenced papers, which is what is the shape of raindrops. So this is the shape of raindrops. When they're very small, they're almost spherical. And you can see, I told you, when you get to close to 8 millimeter, they're the shape of a bun or a idli, whichever way you prefer it. When I talk to Chinese, I say it looks like dim sum. And I think it's North India that's called a momo, right? There is some dish called momo. Like
it's a momo, yes.
Anyway, but when you get into hail, they are almost spherical because hail tumbles even if it's non-spherical, and then it gives. So once you have dual polarization radar, the net result is we could build a picture like this. This is also a picture from my new book. How does rain form? This whole phenomena is explained. Every section of the storm is explained with measurement of reflectivity and differential reflectivity, if you see in this. That's the beauty of this. You get into a CT scan of the whole storm, looking at dual polarization measurements. Let's keep going. Let's keep the hail, because that picture itself, I can talk for 15 minutes. So there is differential dual polarization phase, which is very useful for measuring rainfall. And then it's also more sensitive at X-band. And that's the origin of why we are starting to build rainfall measurement devices at X-band, because for the same amount of rain, it's 3 times more sensitive, which means it's more accurate. And so I'm going to skip this because I just wanted to still talk about infrastructure. And so when you take a dual polarization radar, original single polarization radar that was in Palam Airport had reflectivity and just velocity, if you're lucky. But then when Dr. Ajit Tyagi replaced that with a dual pole radar, suddenly you had too many measurements. People had to figure out what to do with it. That's one of the first problems. Right then, he recognized we have a manpower problem. In order to have manpower, you have to excite the young people. That's why I worked very hard to start this IRAD conference, so that people we have a forum to go present papers and compete for awards and so on. I remember the interesting fun days when myself and Dr. Pradhan sang in a music program in a conference. Anyway, it has all these measurements: reflectivity, differential propagation phase, correlation. All these measurements are available, so we need to make sense out of it. I'm going to skip this again because it's physics. So a simple example, cross-correlation coefficient is smaller in rain-hail mixture or wet aggregates. So finally, if you come back and somebody stopped you on the street in very simple words, without getting into fancy equations, Why do you need a dual polarization radar? It produces better rainfall estimates. It's able to classify different types of particles, that is rain, hail, ice, all that stuff. Of course, you can detect snow also and measure snow, and better quality control of radar data. Previously, when you had reflectivity only radars, the radar was off by 3 dB and 5 dB, nobody would know. This radar, dual pole radar, if it's off and it has issues, it will be in your face because the dual pole measurements won't work. It will immediately know there is something wrong. You can figure out immediately. So, how do these radars have evolved from the early days of big giant S-band only radars? This is our radar. So Colorado State University is a national radar education system area. And I think Dr. Tyagi, I think, has visited here. Isn't that true? Anyway, this is the S-band radar. And you can see inside of the radar and you can see the height of people. This is a very high polarization purity antenna. And then due to the X-band radar is the other system that was built for urban application, because this can be built like a water tank, and then you can deploy it on the rooftop of buildings. You go deploy a S-band radar, you have to get real estate. It needs the involvement of central government. This you can get a private flat operator and then it almost looks like a water tank. This is a research radar that we developed for NASA. This is KU and KA, that is to go with the spaceborne radar. And then I told you this is a small X-band radar. It's on the roof of a building in California. And then this is a shipborne radar. And this is a container deployed on a ship. The main capability of this radar is the ship can tilt and wobble, but the antenna will be very stabilized. And I will talk about that. So this is the CSU C-pole radar. And you can see the radar is deployed on a ship. This actually, we can go deploy it on any ship. So if anybody in India wants to request this radar to put it on a ship for ocean research, this could be done because we've taken this to different places. Right now, the radar has been just shipped for a voyage across the Atlantic. So it'll start from Africa and then end up in the US, crossing the Atlantic, making lots of measurements. This is when the radar was getting deployed in the port on an ocean liner in San Diego. And this, I don't know if, can you see my mouse as I'm moving it? Can somebody respond?
Yes, sir. Yes, sir. We can see.
So that is the shipborne radar on the ship, weather radar, that will not shake with the antenna. So you can see it's the Roger Revelle, which is the ocean liner in which the radar is deployed. That's a C-band radar. So what we did is we also deployed a whole bunch of network of radars in an urban environment, which is Dallas-Fort Worth. Again, it's the urban infrastructure. And I want to talk about infrastructure in a big way. This is city of Dallas-Fort Worth. You can see various places where the radar is being deployed. This is a cell phone tower. There was space on the top of that. We put it there. And this is another radar that's going on another tower on top of a building. Here, the radar is being lifted by a helicopter to go on the top of another building here. And this is radar being deployed on the top of building with a crane. So it's very small compared to these big giant radars, like S-band radars that are sitting in Machilipatnam or Chennai. And all this was made possible because of polarization. If dual pole had not come and taken care of attenuation, we couldn't be building this small radars. This is Europe infrastructure. This is Japan. Japan is filled with X-band radars. This is as of 2012, and since then there's a lot more radars. This is Korea around the city, capital city, and then this is the border with North Korea. And I don't even I have pictures for China. The whole country is full of X-band radars. All cities have X-band radars there. So now let's go to space. So we have now radars, weather radars in space, which is called GPM, Global Precipitation Measurement Radar. That's a dual frequency radar. It's only to make the ground model, we built that ground radar. And somebody made this joke that the total area measured globally by all currently available rain gauges, you put it all together, they said that they will fill a football field or a soccer pitch. So rain gauges are not enough. We need all these instruments to measure rainfall at a regional, urban scale, which is a local scale, or a global scale. And then you have spaceborne observations. I'm going to skip this because this is global precipitation measurement, which has got a dual frequency radar, which is at 35 and 13 gigahertz. And thank you. And somebody made this joke. I took 34 minutes.
Yeah, thank you very much, sir.
I am open for questions now. I didn't want to run late because I teach for a living. So you keep on talking for too long, people will get bored and they will look at their cell phone. Then some of them are not even on their desk. And
So actually question answer session is kept last, but we can take a few questions from this lecture now. The moderator for question answer session.
yeah, it's already 11:30 p.m. here.
Yeah.
Only
So
for this, I like to take the questions now.
Yeah, I invite Madan Sigal from CDHM, Nepal, and Swagata from BAT to moderate on this the question answer session for this lecture.
Dr. Madan Sigdel is not available, so Dr.
Swagata is here. Yeah, I think I made Swagata as co-host.
And there are some questions in the chat. Do you want me to read?
May I read, sir?
Yeah.
Please. Yeah.
One question is.
I can read it. I can read it myself if you want to save time, or if you want to read.
Yeah, that is better, sir. Please.
So one question is, how can we effectively convince local communities about the usefulness and importance of radar meteorology, especially in the context of preparing for response to climate change disasters? We need one good example. This is everywhere, not only here. Everybody, that's what I have seen it happen in other countries. Because my talk is being recorded, I don't want to make too many bold statements. If I was freely talking, I will give many examples that I know. But let me make an example that as we speak, urban radar network is being built in Bombay. And I think Dr. Panditara is here. He's in charge of that. I think if we all contribute and make sure that project is successful, then everybody else will want to have that. Every city mayor will want to have that network. Because we're all very good at copying success, which is actually a good thing. There's nothing wrong with copying success. So that's one answer to me. Then what strategies can we employ? Next question is, what strategies can we employ to spark curiosity and interest in radar meteorology among young students, particularly those in school? How can we make this field an excitable? That's a challenge. As in a university, I understand this. In US, we are like the leaders in radar meteorology, and a lot of people come here. And what we need is, after many years of persistent effort, a lot of people are starting to come to this IRAD conference. Everybody knows when that time comes, anybody who has something to report, the young people will write papers and contest and then put it in. So what I'm trying to do right now is I'm at least working with some of the universities. I have to be careful how bold I can be. I did make a big national plan for radar meteorology education, but somehow that got killed in politics, institutional politics, not national politics. We need prop places, first of all, who are giving degrees in certain areas, and then over a period of time, there should be sustained effort, and then reputation will follow. And it should be any independent educational institutions who have to follow this in terms of syllabus. What I'm trying to say is it's not good for IMD to run a college and then give a degree. That won't work. If that would work, then every discipline will run its own college. Then it will be self-promoting rather than independent. But of course, IMD has to keep a close watch on, let's say for the sake of argument, I have a distinguished professor appointment in IIT Madras. IMD wants to support. Let's step back. How did military radar become very successful in India? That's because when I was in IIT, DRDO invested in guaranteed sending people for graduate degrees in IIT, where they had to go through a program. And these were salaried people who were sent for 2 years and 3 years for a formal degree in IIT. They came and got MTech. Most of them got MTech. That's the proper way to do it. And then they should be forced to go back to their institutions. And then military radar program became thriving in the US. So something like that could be done. And then it's a matter of time before which a private sector will get into this radar. Then it will also pick up because already private players like Google and others are starting to invest in data assimilation from instruments and forecast. That will start invest in telling interesting youngsters. Also in the US, there are programs where people go and give class on environment and climate in school systems. Those can also be done. That's a very good question. This is of importance because the future is in the hands of. I have seen in my own time, right from the first day when that dual pole radar came, Tyagi's worries was, oh my God, Hare Baba, how all our people will learn this? They have to get prepared. And he was the only one who was always worried about that. I was like, what's your problem? Don't worry, something will happen. Anyway, sorry, that's a long answer for a small question, but it's a loaded question.
I think there are some more questions in the question and answer box. Can somebody read it from there?
Yeah, I can read it, sir. So there is one question for 330,000 kilometer square area. How many radar will be needed, sir?
I have a homework problem in my book in chapter. I'd like you to. This is the copy of my new book. I don't know if you can see it.
Yeah, it is visible, sir.
So it's a chapter on. It's chapter 10. The main story is it's not a simple math problem. It's an economic problem, and you have the same square area in Kerala and the square area in Tamil Nadu. The number of radars required are completely different. It's mainly because of complex terrain. So it's that question is addressed in detail in chapter 10 of my book. Nevertheless, city of Bombay needs 5 radars. City of Calcutta needs minimum 4 radars. And Delhi needs 5 radars. Delhi is too big. Like this, I have done some simple calculations. And these are all small radars. So we can go from there. And then can you please give attendance sheet? I don't know what that means. I know what
This
that
is
means.
not for you, sir.
Sir, thank you, sir. There is one more question. Is there any
Calibration of dual polarization radars. Yes. That's a loaded question. It's got a detailed procedure, and there is a whole chapter on that. I please suggest to read. Calibration of dual polarization radar involves calibration of reflectivity, calibration of differential reflectivity, calibration of phase. So there are so many things involved in this. Dual pole is calibrated in so many different ways. One of them is looking directly up and then rotating the antenna. And I'm just answering this very fast, like in the end of an advertisement. Can you please explain, anonymous attendee? Explain what? Is there any standard documents, literature available for design of these X-band radars? That's the document. Then Deepak, just a curious question. If we put radars on mountains pointing down at plains or at lower elevation, can that solve the issue of scarce measurement of higher elevation that you talked about? Well, that's only to a point, because this will go down and hit the ground, and then it won't go anywhere. So, but that will not cover the whole region. But if you cover like this, and then anyway, rain has to pass down, and then you cannot go, that is an option, but you can put a little bit down. But if you put way down, it will just hit ground clutter. And but nice try. How much km the weather radar effectively measure the target? How much km? Oh, kilometers?
Yes.
Considering with Earth's curvature. So, okay, you ask me. For my research purposes, if I do very serious research, very detailed microphysics, I don't use data beyond 60 kilometers. If I'm doing rainfall estimation, I don't use data beyond 100 kilometers. As far as I'm concerned, beyond 100 kilometers, we are wasting our time. And bigger range, this is one degree beams, but this is detailed research, and you might want to make high quality papers. But if you just want a picture, which is infrastructure type, I mean, you have to, when you don't have anything, you can't throw away data. You have to take what's available. And then, so that's an answer for kilometers. What all equipments inside a weather radar? Oh my God, that's chapter 2. Transmitter, receiver, antenna, local oscillator, computer, low noise amplifier, mixer, waveguide. I can just go on and on and on. And sir, is it possible to identify stratiform rain, convective rain, especially on dual polarization radar screens? Short answer is yes. Further, suggest a good book of your dual polarization radar application and design. Here it is. Attendance link, please. How many error, bias, correct precipitation estimation in radars? How to easily correct bias in precipitation estimation in radars? Single pole. Best suggestion is get rid of single pole radars. I think I answered the question fast because I don't want to take away Dr. Mohankumar's time.
Thank you, sir.
I think we should let him talk, otherwise he's been waiting for too long.
Thank you, Professor Chandra. In fact, midnight for you, I suppose, right?
Yes, it is.
Okay, yeah, I think over to you, Dr. Vilas. Yeah, next item is introduction of Professor K. Mohankumar by Dr. Millie Ghosh.
Yeah, yeah. Shall I start, sir?
Okay, yeah, because I don't see Dr. Avilas. So you please introduce Professor K. Mohankumar.
Yeah. screen sharing permission is required, or I can read on my own.
No, where is Dr. Avilas and his team? Please make her a co-host. Body is disconnected. Well, in that case, you can read out.
Yeah. Okay, sir. It's my great pleasure to introduce Professor K. Mohankumar. He is the founder director of Advanced Center for Atmospheric Radar Research, CUSAT, and he has 31 years of teaching experience in postgraduate teaching and possesses 42 years of research experience in the area of middle atmosphere, stratosphere, troposphere coupling, monsoon dynamics, and climate change. He has published more than 115 research articles of high quality in very high-rated, peer-reviewed international journals of great reputation. As a project coordinator, he brought worth rupees 30 crores externally funded research projects to Cochin University from various funding agencies, including famous ST radar project. He has done MSc in Meteorology from University of Cochin in the year 1979 and PhD from Department of Physics, BSSC, University of Kerala in 1984. He has also done postdoc from IIT Kanpur and Perry University, Berlin, Germany. He has a long list of awards and honors on his credit. Few of them are Ashley Choice Award for the book on stratosphere troposphere interactions and introduction, published by Springer. SARC Award for Senior Scientist for Excellence in the Research Analysis and Outstanding Publications in Meteorology in the year 2007. Commission of the European Community's Postdoctoral Research Award in the year 1990. Excellent Category Award for the Indo-French Project by the Indo-French Center for the Promotion of Advanced Research in 2020. At national level also, he has got so many awards. Few of them are National Award for Excellence in Atmospheric Science and Technology by the Ministry of Earth Science, Government of India in the year 2022. H.S. Maharaja Gold Medals adjudging at the Best Research Scholar of the University of Kerala in 1983. And he has so many membership from various countries and various bodies. Thanks a lot, sir.
Thank you. I have given the presentation to the radar center. Abhilash, whether we can upload it?
Yeah, yes, sir.
Yeah, please. Okay, yeah. Well, is it anybody can see it? All the things? Yeah.
Visible, yeah.
Yeah, this is somewhat different what Dr. Professor Chandrashekar talked about the dual polarimeter radar. This is an entirely different type of radar, that is a wind profile radar. I think in India, I think we have got the in Tirupati, we have got the ISRO, we have got an excellent 53 megahertz radar. Then afterwards, we have got in Sriharikota, then 47. Then thereafter, the government of India has planned for a series of radars in India for the better improvement of the weather forecasting. So they planned under the Department of Science and Technology. Can you go to the next, please? Please, next. So I think just before, yeah. So actually, what is atmospheric radar? It is quite different from what we have seen earlier. Atmospheric radars, they are also known as the wind profile radars. It is actually this vertically directed pulse radar. It is capable of analyzing. We are sending signals and backscattered to determine the velocity vector of air in the beams. And it is interesting that in meteorology, especially in atmospheric science, there are the most important parameters of vertical velocity. In most of our conventional instruments, we are not able to correctly measure or detect the vertical velocity because of the instrumental error. But the radars, wind profile radars, can accurately give the vertical velocity, which is the most sensitive element of the weather. And they are dependent on signals scattered from gradients of the radio refractive index associated with turbulent eddies, because the radio refractive index is an important factor that controls the that can detect the turbulent eddies in the atmosphere. And the Doppler shift in the backscattered signal is used to derive the wind speed and the direction as a function of height. So there are two methods we can find in using the radar. One is the Doppler beam swinging method, and another is the space antenna drift method. In actually, they are very common that it depends upon the type of observation we need. Mainly, we are using the Doppler beam swinging method. Yes, please. Next. Please go to the next, because I'm. So, what are the applications of wind profile radars? Because for the operational purposes, we can do the forecasting, and also it is very good for the aviation purposes. Wind supports for satellite launches. That is especially we are doing in the Shrigota also, we are doing similar thing. And air quality meteorology measurements, that is also this can be used. These are the four different types for operational purposes. And also for the research purposes, we had to study many things. We can study the boundary layer processes, what is happening in the lower layers of the atmosphere, and what about the turbulence. And depending upon, we can study about the stability of the atmosphere, convection, storms, and everything we can study, and also what is the precipitation. And we can study the stratosphere, troposphere exchange, and the vertical velocity. And also it can be used for the defense purposes. I think that is also another interesting application, which we are, of course, we are not using that, but it can also be used for the our strategic purposes also. Next, please. So actually, the wind profiler radars are basically classified according to that. In the boundary layer radar with a frequency of 900 to 1500 that frequency, megahertz frequency, and lower tropospheric radar 400 to 900 frequency, and tropospheric radar 200 to 400. ST radar, actually it is a that is in the 50 to 200 and 40 to 60 range that we call it the mesosphere, which can go up to the mesosphere. The average the power pressure is about 100, 1000, and also minus actually for minus 100, and 5 into 10 to the power of 5, minus 10 to the power of 8, and also it gets 10 to the power of 8. And height coverage, that is the most important, which we are also looking mainly. The boundary layer can go up to about only 1 to 3 kilometers. And also the lower troposphere radar, it can go up to 2 to 6 kilometer height. And the troposphere, it can get 0.3 to 15 kilometer. And the ST radar 0.5 to 20. And also the MS radar, it from 2 to 20, or sometimes it can go up to 20. And also in the mesosphere region, also 60 to 100. And also in the ionosphere also we will get in all cases, but it is not mentioned here. And the resolution of the height, measurement height is, we can see in the boundary layer, it is 75 meter. It is 100 meter for the lower troposphere radar, and the tropospheric radar 150, and stratosphere 150, and there is 150. But we will get a much better resolution also here. And the time resolution also we can take in 10 minutes, 10 seconds, 10 seconds, almost in around 10 seconds. Next, please. Then the question is, so far all the radars are mainly concentrated between 50 megahertz, that is ST radar, MS radar, 400 megahertz, that is all the boundary up to 12 kilometer region, and 1000 megahertz radar, that is the boundary levels. This is the conventionally available wind profile radars throughout the world. But a feasibility study conducted by NASA for monitoring the space shuttle launch time, they suggested that, there's in a paper, they suggested that the 50 megahertz, 225 megahertz, and 400 megahertz are possible for stratosphere tropospheric studies, or stratosphere tropospheric coupling process, or it can go up to the stratosphere. But why 220 that are 200 range megahertz are not available in the so far? Mainly because it is the frequency is not available for the for our radar purpose, but it is used for the radio and TV broadcasting So this frequency is not allowed earlier, but now it has changed. It has changed from to the digital thing. The frequency is now open. That is why our idea of the 200 megahertz radar is coming to the mind. Especially in India, I think especially we can thank the G. Vishwanath sir, and he is so much particular about the 200 megahertz radar work. But many places he tried, but they are not accepting because it is a new one. Nobody want to make any risk. Next, please. So they tried first in the Nainital, but it was not successful at the time. So now from the paper by Balsley and Gage is published they showed that fact are the factors influencing the choice of a radar. They have got the existing radar frequencies that we have seen, that is 500, that is 50 megahertz or 30 to 60 megahertz. That is what we can see in the left-hand side. And then there is the 400 megahertz, right? Like that, the frequency is available. But around 200 megahertz radar, there is no radar as used. It's similarly about the weather radar frequency is different. And also the dish antenna, there are other radars are different, array type of antennas radar. So different, no radar, I think in this range is lying in the near of the 200 megahertz. So initially we thought it was a risk to go for the 200 megahertz radar because it is essentially even several our committee experts are also suggested. This is the first time you are trying for the 200 megahertz radar, but there is some doubt whether it will work or not. So that is why purpose in our mind. Then the another option is to go for 50 megahertz. But when we go to 50 megahertz, especially our aim is to study about the dynamics of the monsoon, especially in the monsoon low-level jet stream. It is height of the jet stream is only 1.5 kilometer. If you go for the 50 megahertz, we lose it because 50 megahertz radar cannot detect below 2 kilometer range. So we are not able to find the monsoon low-level jet. So we took the risk. We can go for the 200 megahertz radar, which is possible to get about 0.5 kilometer or 500 meter above, we will get it. That is why we took the risk. Next, please. Next slide. So what is the maximum? Then another question is how much height it can cover. There are a lot of doubts during the discussion that, especially when we come to the 10 degree north in Cochin, the height maximum, the troposphere height comes to about 16 to 17 kilometer. So we have to go to the troposphere, stratosphere means it has to cross the 17 kilometer. So then it is quite risky. But if in Nainital, the advantage is that it below the bottom level itself is about more than 2 kilometers. So, and the troposphere height is also less. So it can cross it. Then the problem is that again, we took a risk. And even there several members are also suggested it is a risk if you take the 200 megahertz in Cochin, near to the equator, because there is a possibility that there's a possibility it won't go to the lower stratosphere. Okay, next, please. So next. So then we calculate the vertical profiles of the atmospheric structure, the atmospheric, that is the structure constant. Refractive index structure coefficient, we measure the profiles used on the radio sound observations available in the naval base in Cochin. Then we plotted all the mass. Then we can get the profile. From the profile, it is possible that the signals can go even turbulent. Based on that, we found that the atmospheric turbulence, based on the turbulence on different seasons, we have not that, yes, it can go up to 20 kilometer in all seasons. That is what we have got the result. Next, please. So now the merits from the 200 megahertz radar, that is the noise from the external sources such as galactic, that we can have seen that picture, or cosmic noise, which are the important consideration for radar operating in the frequency range of 50 to 1000 megahertz. The galactic noise for a frequency of 50 megahertz over the near equatorial region is around 6000 Kelvin, whereas it is only 1000 Kelvin for a frequency around 200 megahertz. That is one advantage we got. And then compared to the 50 megahertz radar, the 200 megahertz radar is less affected by cosmic noise. So that is one of the advantage we got. Moreover, radars operating in UHF ranges are known to get saturated under rainy conditions. Like 400 megahertz, if you go for that, it is more on rainy conditions which you will get. And while such issues do not affect radar in the frequency of 200 megahertz. So in fact, it is a trade-off between the existing 50 megahertz and 400 megahertz that we are commonly using radars in terms of galactic noise, cost effectiveness. The expense also comparing to 50 megahertz, it is much less. Physical size of the antenna and better vertical resolution. Resolution also will get 45 meter here. And height coverage, it can go up to about 20 kilometer, especially in the it can cross the tropical tropopause, and that is around 17 kilometer. So that is the advantage of 200 megahertz radar. That is initially we studied. Next, please. Then the Cochin University of Science and Technology, then the government of India has a plan under the IRFA, that intensification research in high priority area that the Department of Science and Technology has allotted. They want to have installed 10 radars in India at the time. It is in the early century, around 2006 or something. They had instituted. They have got a lot of meetings they conducted. They thought that we can have a plan this type of radars in India. Then first they conducted in Calcutta, then we went to the Tirupati, then we went to Trivandrum, then they came to Cochin. So different places we presented, and then they selected Cochin University of Science and Technology as the first place university you can start at 200 megahertz radar. Then we applied the frequency clearance, because at that time it was 200 frequency is not very common. We faced a lot of difficulties in the WPC, but we got it clean and cleared. And then the advantage is this 205 megahertz. We got the allocation of frequency, and we designed the expert members are suggested for the designing, and the data patterns India, they are developed and fabricated in India. So in 100% it is an indigenous thing. So developed and fabricated in India. It has advantage of it can work with 20 all the time. We are also used for 14 days continuous operation. We tried that before handing over from the company. We had to give a test for continuously operating radar without stop for 14 days. So then we have known that the radar works. Now it is also. Economically also, radar is the cheapest of the, when we are taking observation, every day if we are taking radio sound observation all the days, all the time, comparing to that, this radar is much cheaper comparing to the cost of the radio sound continuous observation. Next, please. This is the aerial view of the 205 megahertz radar at Cochin. It is quite interesting that initially the DST has suggested that we can have an antenna at the top of the thing so that it is very compact. So 619 antenna elements are there displayed. And then we have all the transmission receiving modules are just below that. I think I'll show in the next few slides. So, and the other matters are researchers and officers are all in the lower. So first this is the aerial view of the radar we taken. Yes, please. Nothing you have mentioned, height coverage. The advantage of this, we asked for a 500 meter and above. That is, we don't know whether we will get. But in the final part, we got it. The radar works from 0.315. 315 meter onwards, we are getting the resolution. And the good resolution of 45 meter. So here, the lower atmospheric coverage is far, far better. And it can compare to, comparing to 405 megahertz, it can go below. And power consumption is much less here when we are comparing to power consumption. And it is highly cost effective comparing to the 50 megahertz. Next, please. Next, please. So this is the location map of the ST radar. We can see that it is Kerala and in Cochin is one part is located in the Arabian Sea, and next to the other part is the Western Ghats. So it is only just 100 kilometers to the east of the Cochin. is the Western Ghats. So it lies between two different physiographic features. One is ocean, always having the monsoon. Our basic idea is to study the monsoon characteristics because this is a gateway of Indian summer monsoon. That is an advantage. And also we have get to the mountain and next 100 kilometers on this terrain. This is a beautiful area for the scientific studies for this purpose. Next, please. Next. Please, next. So the sign that thing I already mentioned here, the Western Ghats on one side and the other in the highest mountain range, Anamudi, highest mountain range of Western Ghats is just 100 kilometers. Same latitude belt of Cochin, we can see. So we can study many things because orográphically induced gravity waves, we can study planetary waves, we can study all these, what forcing which we can study. This is the advantage of this region because the moist air coming from the Arabian Sea is lifted by the Western Ghats is very easily we can study using now we are studying that is using the advanced scientific methods. Please, next. So this is specification. I don't know whether it can read it. All the frequency specification is frequency 205 megahertz. It is 5 megahertz is bandwidth. Type of 619 elements or active phased elements, array elements are there in the transmission and also the similar transmission receiving TRM. It is a 3-element Yagi Yuda antenna you are using. And height coverage, we here asked for 500 meter, we got 315 meter onwards to 20 kilometer. Range gate is 1024 programmable. Modes of operation, we can use in DBS and SAM mode, but we are basically using the DBS. And height resolution, because we are getting better lower atmospheric height. So DBS we opted. And height resolution 450 to that is also tunable. And beam width is about 3. And zenith angle is 0 to 30 degree in range of programmable. Azimuth, it can rotate all the angles of 161 or 360 degree with 1 degree interval. And then the pulse mode is 0.3 to 26.8. And binary phase. Okay, that are all the technical things which we can use, and anybody want they can refer these, and all these detailed specifications are here. Okay, next please. And this is a block diagram which we have got the antenna, we have got the TR modules just below that, and then how the transmission and this the distribution network and 600 wind profile radar, and all for engineering, those who are interested in the technical part, how the radar computer which transmit the signal into the UVW. Finally, you come to the UVW, that is east, west, north, south, and vertical wind components are also given here. Next, please. This 600 Yagi block diagram of TR module, how they are reaching. So we are going to each antenna, we have got 1 TR mode directly to the cable. Next, please. Then we have the accuracy of the testing. We do the moon tracking for point accuracy. That is also the one-day moon rise to moon roll. And we have got the cross-checked with this is also given in every night. So please next. And before starting the 619 elements, we have got a doubt whether it will work or not. So what we use is we first we start a 49 a mini profile radar we planned a nearby building to that building. We constructed with the same type of specification or details with a 49 element mini radar is estimated. And the engineering scientific that we want to know whether it will work in the engineering side or also scientific side, whether it will work. And then we tested all the parameters, all the same way what we have the main radar we tested first here. The mini radar is used to validate the function of all the subsystems of ST radar as well as the signal processing system. And then we got the result. That is the expected height coverage for the 49 element mini radar is from 4 to 6 kilometers. We got it. And we got a thunderstorm activity also during the mini radar experiment we conducted. That we have got excellent results we got. Next, please. Next. So this is the then what we are doing. Even after taking the mini wind profile radar, we want to comparison whether the data is the reliability of the data is the main thing. So we requested the NARL thing, they have got the portable or mobile lower atmospheric wind profiler, they brought here. And we cross-checked the radar observations from the same position. And also we have got the co-located radius field observation from the same site. So that all the three, that is our mini wind profile radar, our lower atmospheric wind profile, NARL, and this our radar radius field observation we compared. And we got that the radar, the mini wind profile radar is matching, and the data is of good quality. It works. So that the radar, the 205 megahertz radar works. Thanks to Dr. Jayaraman. At that time, he was the director. He expert all the steps to take to bring the lower atmospheric wind profile radar from NARL to Tirupati. Next, please. So this is the prototype 49 element. In the picture, you can see the left side is the 49 element prototype and the main radar. Then we afterwards, even after the clearing that everything is perfectly all right, then we shifted the radar. Then we have started the work on the 619 element in the new building. That is a very circular element, about 32-meter diameter at the top, having all the facilities, all the places for the 619 antenna, and then the TR modems. Next, please. So this is the one they came and checked. All the groups are here. The DST, Department of Science and Technology, they're also there to verify. The technical committee also there to verify whether this is the functionality, the accuracy of the radar system. So they are all satisfied. Then after their recommendation, then we had got the next. Next, please. So this is the aerial view of the, we can see the, from the top, how the antenna is distributed. It is the signal, the antenna of the 205 megahertz on our radar center. Next, please. This is the 3-element Yagi antenna, and you can see in the bottom of that. This is the top, is that is the rooftop terrace, and just below that the roof. We have got to the hanging type of transmission receiving module, so that we will actually the loss of power is reduced, or the loss of power from the radar and the antenna to the transmission receiving module is minimized. So that way we can directly, each one has, we have a lot of studies we made, how we can, without water intrusion, how we can do, we put a J tube in it. So the cables are put inside, and lot of homework and lot of discussions. And then in the transmission receiving module, it is get heated up. How we can reduce the heating, that also we took a lot of discussion. How we air condition, if we put, how the air condition is basically cooling in the lower level, how it can go up to the upper high, how it can transmit to the upper. These are all, we have done a lot of thinking and discussions and many way. Then we have got arranged. And it is now a fully under the environmental conditions. The transmission receiving module works. Next, please. So the configuration is actually the technical thing, the order of -120 dBm to -160 dBm. That is signal one deeply buried in noise. And pulses compression algorithm is implemented in ST radar to increase the signal to noise ratio and without compromising the resolution in range. And ST radar also has got the provision for programming as a coded and uncoded operation. The code length can be up to 1 to 64 bits in steps of 2, and baud rates are 0.3 microsecond to 0.4, 0.3 micro, 0.4, 0.6, 0.9, 1.2, 1.5, 1.8, 2.1, and 2.4. To improve the SNR, the other techniques need coherent and incoherent integration techniques. The number of coherent integration that can be preferred, one from the 1 to 1024, and for incoherent stand, it is from the 1 to 128 type. These are the configuration work. Next, please. Then because now we are getting the data. Initially, we got a problem that the height of the altitude height is we are not getting up to 12 kilometers. Then Dr. V.K. Anandan from ISTRA, he came here, he stayed there in the radar center, and he had given that with his lot of work. He has shown that the signal will get height up to more than 20 kilometers. Even some of the good rainy seasons, even now monsoon time, now the monsoon time, now we have got a good rain time, it goes up to 24 kilometers. That is the advantage of the height resolution we are getting on through the season. There is no, I think nothing, it is coming below 20 kilometers. That is the advantage of the 200 MHz radar and the single pulse. This is we are putting the balloon launching from here. Next, please. Next, please. Next. Hello. Next, please. I'm not able to.
Their connection seems to be lost. Could you please wait for a few minutes?
Okay.
The host connection seems to be lost. Their video is also frozen, it seems.
Okay. What I have to do? I have to do something here, or you do something, you do there? So actually it is uploaded from the ACARR. So please check it. So the radius on the observation that we are taking every day. And what we have done is during the all the time observations, we do continuous observation. Radar operation also, when radar is operating, we are also taking observations continuously. For example, if you are taking 2 o'clock radar observation, we take radius on observation about 2-3 radius on observations also we are taken in between. So the height resolution also we are found to be matching. And that I want to show in the signal. Then what we have done is we made studies on how the data is data taken from the radar and how the data taken from the radius sound is working. Radius sound observation, what we took on those days, we are not given to the radar the data patterns. We ask them, you give the wind profiles from your radar, from the radar alone, then we will cross check with the radius sound without. We are not given to that. So that we cross checked it. Then we found that it is in very good correlation on the number of samples and the accuracy is very good. That is why it becomes more reliable in the radar data. So what happens, I think whether presentation is...
yeah, they have come back.
Yeah. So this is actually the radar. Then after getting the complete clearance, then we have gone for the quality of the data. We checked, we have studied the different aspects. Then during the rainy conditions and the dry conditions, our conditions are also we have seen that the signals are quite different. In 205 MHz radar, we have seen that 2 signals are shows entirely different type of signal. So that the moisture precipitation pattern, it becomes, we can easily distinguish. That means, so that's the advantage of the, what we have seen in the 400 MHz that we also can see in 200 MHz radar. That is in the precipitation pattern on the radar, that is giving very accurately. Okay, then this is the comparison of derived horizontal wind from radar and from the radius sound. We have seen that it is matching very well, almost without anything, and there is some, we have made all the corrections and without giving to the radar the developers. We ask them to give the profile. We will cross check with the radius sound with our own. That is why we could find. Okay, next please. Next. Okay, then we have checked the accuracy zonal wind. We can see that zonal wind is almost to have a very high correlation, and of course, meridian wind also almost the same good correlation. Next, please. We have then checked the please. Next, then we have put the validation in profile. GPS radius sound also we calculated the difference between these. Okay, next. Next. This is the height coverage found to have that we have to the maximum height coverage. All the months of any year, we have cross-checked with the January to December. Almost we are getting about nearly 20 kilometers. Of course, no problem with the signals from that. Even though we are getting a special advantage, maybe most probably we are in the coastal region. A lot of moisture contained in the Cochin region. Next, please. Then we have studied the monsoon circulation about 2017. The left we can see the evolution of the zonal wind and rainfall in 2000. Of course, everybody knows that 2017 and 18 are the heavy rainfall days. in Cochin, in Kerala, floods are there. We could take some of the observations on that. Earlier in August 18, we could close it because of the heavy rainfall. Otherwise, all the observations we took out from the radius on the radar observations. Next, please. Next, this is about the 2018, and that also we got it. Please, next. The radar of the, now we have got a thunderstorm. I think first we took the mini radar about the 2 thunderstorms in 21st April 2015 and April 24th April detected. And these during thunderstorm, even it is the time also we have noted have enhanced height coverage before, during, and some other sometime after a thunderstorm. This what we have studied in theoretical thing which we can easily see in our own observation. This is on 14. On that day, even 14 in element, it goes up to 12 kilometer height because a lot of moisture is involved. Next, please. This is a normal, this is the earlier previous one which I mentioned is about the mini radar, but the main radar also we had some experiments on. Of course, thunderstorm activity, everybody knows. Okay, okay, this is the signal, what we are getting the signals from before the radar, before the, and then the occurred on 24th and 5th May, observed on main CUSAT radar, how the evolution, we can get the profile from where the moisture, the signals or the what we are getting, the spectrum, what we are getting in the heavy radar. We can see the before starting the radar, the development, the beginning, development, that is the growth, and become mature, and then gradual decay of the radar system. We can study from, we can easily identify from these continuous observations. Next, please. This is the pure plot of the horizontal winds during severe thunderstorm, which we have seen. That you can see how its evolution of the wind structure, horizontal wind structure, how it varies. And when there is a thunderstorm comes, how it behaves. Then we can see after that the this can be done. Next, please. I can just I go more clear in the next slide. I can see that we have first we have the beginning before the beginning of the thunderstorm itself, there is a change in the wind direction. Then there is a lot of vertical variation. The growth of the thunderstorm development is going on like this. Then once the thunderstorm matured and after the rainfall, when the rainfall starts, it gradually, you can see the rain started at 6:15 hours and rain ended 21 hours, 22 hours. And afterwards, gradually the wind become normal after the event is occurred. Yeah, see, well, before the time itself, we can say. Next, please. Yeah. So I think we have given the turbulent convection boundary layer is around 1.5 kilometer before the storm. But there itself we can find out. Then enhanced horizontal wind in the free atmosphere that you even can see in the level. And the turbulent activity increases the height even in the free troposphere that we have seen the blue circle. Indicating that the atmosphere becomes even more unstable to higher heights just before the thunderstorm. And rain starts at 6:15 hours and last up to 21 hours, that green circle. And lower atmosphere returns to somewhat stable conditions during the post-rain event. So next, please. So now this is what I have shown is up to the lower level. Now in the stratosphere or at 20 kilometer height, we can see how the penetration or the forcing of the thunderstorm time, the wind can vary even up to that can change up to the stratosphere, in the lower stratosphere. And there also we can see there is a gradual, it's stabilizing is taking place in the even upper troposphere also. Next, please. And this is very important because this type of radars are very important for understanding a clearer turbulence. What he has observed in May 20th, I think the UK-based, Singapore-based Singapore flight suddenly into the air pocket. I think similar, if you had actually a wind profile radar in between, you would have easily identify this type of thing, the type of like this, what we have the breaking of waves, how so air pockets are very commonly forming, and then it can cause the sudden fall in the that can cause. Thereafter, we have studied the diurnal variations of monsoon circulation during active and break phases. That also shown here some of the things how in an active phase, what is the height of the LLJ, and we can study about the position of the LLJ and position of the TJ, and then what is the difference between and how they have become, because during an active phase, we can see that the low level jet become higher and the TJ become less. And in the break conditions, TJ becomes more, TJ becomes higher and LLJ becomes lower, which we can easily identify from this radar. And evolution of atmospheric boundary layer also we can see, because Cochin is located near the coastal region. It can easily identify the land and sea breeze pattern, breeze formation, development, and at what time it can happen. We are continuously operating the radar, operated continuously for 4 days in the month of January, and 4 days in May, and 4 days in April in 2000. And we have studied about how these pattern tidal variability of the tidal variations and land seas variations of the thing that also we have studied during the pre-monsoon time. And we have studied how the two zonal wind distribution, 2 consecutive monsoon years. One is in 2017 and another is in 2018. How it varies, and the lower level we have shown the rainfall and also the strong TJ behavior, and also TJ extension. And Doppler signature easily monsoon rain June to 3 consecutive years also we have studied. That is the beginning onset time during the signaling. The Doppler signature of the monsoon phase is easy, that we can see that how when during the heavy rainfall time, this suddenly shows a drift. This goes the water vapor. Another is that now we have studied the inertia gravity waves over Cochin. So they can detect between the altitude range of 14 to 20 kilometers. The waves occurred at a time when deep depression prevailed. We have studied, we have to put continuous observation again for 72 hours or something, when deep depression prevailed over the Bay of Bengal. And the source of wave is most likely deep convective associated cyclonic activity. And subsequent studies of this nature from the radar facility are expected to provide deeper insight into the internal gravity waves observed over the tropics. Next, please. And this is the time height variation of zonal and meridional wind observed for 22 to 27 October 2016. That is, we plotted all the zonal and meridional wind, and the perturbation of zonal and meridional winds at 26 October. Okay, next, please. We have seen that there is a wave type of the wave detection of inertia gravity waves in both wind speed and direction in the zonal and meridional. So next, please. The intrinsic period is what is the characteristic inertia gravity waves is 28.75 hours is the intense period, and horizontal wavelength is about 1,221 kilometer. Vertical wavelength is about 3.74 per kilometer, and group velocity horizontal 9.73, and vertical group velocity is 2.98 to the power minus 2. Next, please. Then estimation we have, because the tropopass detecting using a radar also we tried. Next, please. Go ahead. So we have used the methodology to find out the SNR from because we want to get the temperature. How we can the wind from the wind direction or the height. How will you find out the hold point tropopass height? So we are using the gradient of SNR used for CPI. And the radar radius on that. Then we have got, after calculating all the CPT height from the SNR values, we compared with the radius on the CPT height, the temperature of the cold point tropopass of radius on the it giving almost very good signal about that. The CPT calculated from SNR data of the radius on the radar and the radius on the XR matches very well. Next, please. And the way we have seen the variability of CPT height during the monsoon season also we plotted. Okay. Then the Doppler power spectrum of a zenith band observed during the rainy day of 13th May 2017. How changes in the low. There are a lot of studies are open, areas are open to study about this area, about the thermal structure. And rain observation on 18th May at 2 p.m. to 8 p.m. continuous observation, the development and the popping. Then our radar data, because we want to AULS, they asked what they want to compare, validate their data. They asked us to give our own data, and then we made a study. Of course, AULS, everybody knows that it is a satellite, only European satellite. They are capable. They want to study the wind profiles throughout the world, because it is very useful for the study of using for the forecasting. Then we have the scatter plot between radar and AULS wind speed. That's almost very good. And this also published, all this work. Then Stratiola, there is a free balloon, that is balloon on the stratosphere that is moving along our, is that NASA, French American project. They also asked our data to get it verification of the data. Okay, next please. During the meteor, in addition to that, we have the meteor passing, also we can detect from the radar. Okay, next please. And also there is an SNR, previous SNR plot north beam and off zenith angle. During a thunderstorm, when we can see there are some signals even in the ionosphere level, lower atmosphere cell, and spike of the blue jet also we can see from here. And we need more and more studies using observation from this type of observation. Next, please. And also, during again, interesting to me is there is which we want to do further investigation on that. A precipitation-like spectral pattern observed in the upper troposphere also we can see in associated with the thunderstorm event. Next, please. So that is a water vapor intrusion is observed at the thunderstorm from a lower height to a peak of 12 to 15, 14 kilometers. Of course, the water vapor quantity is much less in that level, but we can see some signals like that. And what is the reason? I think we have to be further studies using continuous observation. Then we have got, and then another interesting thing is everybody told that ionosphere, 200 megahertz radar, ionosphere is not possible to get. Even our own, our experts told that, ionospheric expert, they told that there is a sub-meter scale system, it will work. Even then, I got a curiosity at that time. I asked Vishwas, sir, I want to get the ionosphere. Is somebody want to do in future? He told that he had to orient the antenna in the geomagnetic east-west north and latitudes. So before that, installing the radar, we put the antenna in the geomagnetic orientation. So we are beautifully getting the ionospheric observation. Okay, next, please. I think go ahead. I think these are the testing that we had the E layer signals you are getting. Go ahead. 20th May 23. Next, we get another E layer observation we are getting on another day, and F layer also we are getting. So F layer. Next. And F layer we are getting. And this, it's an interesting thing. We have seen that during the Tonga volcanic eruption and associated tsunami on 15th January 22, we have got beautiful observation on the ionosphere. And this is repeated after 24 hours. There is, I think the paper is also published, an interesting work that is published in the Of course, this radar is possible because of the Department of Science and Technology under Science Engineering Research Board. And I would to thank Dr. B.M. Reddy, is the chairman of our radar facility in India. He took a lot of it. Vishwan sir, he has given the confidence to go ahead with the 200 megahertz. Of course, Sanjeev Rao, he has also helped a lot. We can then technically also, he done a lot of things, he helped us. He come and stay in the radar center, even night, and then you do that. And Prof. K.V. Janardhanan is the chairman of the technical committee. Jayaraman, so former director. And of course, KP Ray and many other expert members are also there. And I'm here to thank the Data Patterns India Private Limited, Chennai, even for the design, development, installation, realization, maintenance, and the quality of the instrument is excellent. I think it is even actually the degradation is much less. Every year we have the antenna or the TR module failure is much less, only less than 5. But comparing to many other places, it is very high. And of course, the later, after the 5-year period, Ministry of Earth Science is agreed to give us, and University of Science and Technology is giving the sustenance. Thank you. Thank you.
Thank you, sir, for the exhaustive presentation in this short period of short time, presenting our history and capability of our ST radar installed in Cochin. So now it is time for a question answer session. I request Dr. Saguda and Dr. Madan.
I'm here. Yeah, last time I missed it, but this time I'm here. So thank you. Thanks a lot, sir, for these details of the radar. Truly speaking, just I was discussing with my student that this subject may be very less people in meteorology field will know. So this, I think the whole course is very important for all meteorologists. I have received now 4 questions, but I am sure that when time grows, the number of questions will increase. So from the Zoom, the question from Dr. Sweep Rambat. What is the range of wind speed that able to be recorded from 205 megahertz radar? 205 megahertz.
Yeah, you are asking about the frequency? No, what is the question? It is,
The question is simple. What is the range of wind speed that able to be recorded? That able to be recorded?
It can go up to about 60 meters per second also, it can detect easily without any problem.
Okay. Thank you.
Because in Cochin is not that much, not much strong wind speed, windy area. But we get landed, especially in the monsoon low level and STJ, that we can easily. So far we have is much wind speed, I think can go ahead.
Yeah. Another question from Manik. What are the limitations of ST radar?
Yes, one of the limitation is we won't get below 300 meters.
Here is an extension question also. Further, if these radars installed along Kerala coast, will they useful for tropical cyclone tracking?
Tracking is not possible, but we cannot find. We can find the wind, the dynamics when we passing through that region. Just like I have shown the thunderstorm activity. We similarly, when there is because it is tracking, it is not a tracking radar. It is a radar which can detect the stability of that or the disturbances which is causing in the atmosphere.
Thank you, sir. So now I'm taking 2 questions from YouTube. Then again I will come back to the Zoom. And the question from Gauripati Bhabilala. The question is little interesting. In urban environment, how multiple radars correlated as one output?
Here the wind profile radar, we have to, you are asking about comparison with the other thing or matching with the other radar?
If we put multiple radars, so maybe he wants to get a single output because instead of individual radar, maybe it would be noisy for him. So how to correlate as one output?
That gives a very good spatial distribution of the wind structure. If it is a single point, we will get only the vertical variations. But if you get a multiple type of similar wind profile radars, but it gives a beautiful distribution of that. We tried, actually, we made a comparison with our studies using the Tirupati radar, Cochin radar, Calcutta radar, and this Guwahati radar, Nainital radar. We put all together. We took observation during the time of the monsoon break and active phases. Then at that time, different places in our country have a different physical characteristic. Having wind structure, I think we will get all the wind structure in the same time. But the problem is that at the time when we are operating, some of the stations are also not able to get that quality of data. Tirupati and our data, I think, matches very well, and also we have. But many other places, the error is somewhat not able to match. But there is some problem arises. We made some the mutual study about all the wind structure of the country using all the wind profile radars in India.
Thank you. Sir, another question from YouTube, Iara Masu Sudhir. Antenna backscattering range is beyond the harmful range. How to overcome it?
I think our engineer experts, Titu is there, he can answer that. The Ragesh also, whether we can say that. Give some. Yeah, we will answer that because I am in the science field.
Sir,
technically. Okay. The question, please repeat. You can see the question, is it?
Yeah.
I can repeat again. Antenna backscattering range is beyond the harmful range. How to overcome it?
That we are using a thing like Faraday cages, which will block out the radiations from the side lobes as well as the back lobes. So according to our frequency of operation, we can design our Faraday cages, and it can be put inside our ceiling concrete, and it can block the radiations to somewhat extent. So that can be put around the radar also. So that can also block the radiation going from the side lobes. This will also increase the signal detectability of the radar also.
Thanks a lot. Yeah. So people can be saved by this. And another question from Zoom, from a radar image, example 40 kilometer, 10 minutes images, can anyone extract the wind speed and wind direction? And if it is yes, how?
Joy here. Data processing. This question also data processing.
40 kilometers, 10 minutes image, can one extract the wind speed and wind direction? If yes, how?
Yeah, for the 40 kilometer spectra, we will be getting different layers. That is, different range bands will be having different peak power. So we need to pick the exact peaks of that power, and we can map that power, and we can find the moments. From that moment estimation, we can calculate the UVW components. From that UVW components, we can find the wind speed and wind direction.
I think this is pertain to that DW radar.
I think this is more for
40
the
kilometer and 10 minute images. Yeah.
Yeah, the next question is from Vishal Juneja. Mainly his question is that how, when the studying of internal gravity waves above troposphere, which you have discussed, and how it can be directly useful.
Yeah, that we can study about how the internal gravity waves are generating here, how it affects the weather systems that we can study. Because you see, I mentioned that there is a cyclonic system which formed in the Bay of Bengal. Bay of Bengal, that causes a disturbance even in our tropical region, in our near equatorial region, the coastal region. So that type of weather systems, how we can affect on different areas, we can study on the wave activity in different places and to understand the monsoon dynamics, the dynamics of the region, atmospheric dynamics.
Thank you, sir, to all the participants, because they have asked the questions. I brought it here, but now any panelist, if you feel any question, can interact directly with sir.
Yeah, we can send any message, we will answer to it.
So there is one more question, sir, one moment. There is one more question. What's the main reason that we cannot access the mesosphere with 200 megahertz radar?
Yeah, actually that is the question. You even see all the radar signals, it can't go beyond the 25 because they are quite weak. Getting the reflection in that region is quite weak because that region is called the radar blind region. We are not able to get the signals especially from 30 to 60 kilometer. It's not at all possible to get the reflection. You know that the atmospheric structure is like that. The temperature is decreasing, that they are increasing, and then from the stratosphere region to the above, we would get the reflection. Highly stable region, and that is why we are not getting the signals in the signal.
So next question is there any way to study mesosphere? Is there any way to study the mesosphere by radar? The question is little
I think using the MST radar, we can start using the MST radar, and rocket observations we can easily find, and also the low flying satellite also we can measure the winds in the mesosphere. Earlier they are using the meteorites movement. They used to study about that. Now we can directly measure using the rocket. That is why in India under the Soviet and earlier in the Soviet collaboration with the Indian and ISRO, we have got every week we are taking observation every week. But now because the Soviet Union is no more, they are not taking any observation level.
Thank you. So I think all the questions are well taken. And now, if there is any question from the panelists, anyone can ask directly from the panelist. If there is no one, so I'm giving back to Dr. Avilas. So now you can proceed further.
Yeah, I think if now I request our advisory panel members Chairman sir, Pradhan sir, to have some comments.
Is he available?
Yeah. Sorry, I was just making it unmute. So, our sincere thanks to Professor V. Chandrashekar, Professor Mohankumar for their very encouraging and educating lectures. Truly speaking, this is that's the beginning of radar training here, and we hope that we will be in the rhythm as we have planned that every Saturday we will be having the lectures from 3 to 4 p.m. and subsequently that will be followed by the question answer session. So hope that more and more number of the participants will be joining gradually here. So from 1st June onward, we will be focusing entirely on the radars and all different kinds of the Doppler weather radar, single polarization, dual polarization, their products, their applications. And here in the applications, the one part which is very interesting is here. The earlier stored sequences will be analyzed one by one, that whatever be the thunderstorms, hailstorm activities were there, what were the signatures, what were the winds associated with those systems here, and how much destruction they can cause. So in fact, Doppler weather radar is one of the most indispensable tools in addition with the satellite. I don't say that standalone it can do all the things, but as far as the nowcasting is concerned, in the next 3 to 6 hours duration, if you want to see that where the thunderstorm will be initiated, in which direction it will be moving, and so on. So those things now we have to start with from the 1st June onwards. And what I wanted to say that all the presentations will be shared with the participants, so that before coming to the lecture, they can read the presentations and they can ask the questions just after the lecture. So it is my great pleasure that I have been given the chance to speak on 1st June as the first lecture introduction of the Doppler radar and so on. So thanks to everyone, thanks to Someshwar Das ji and President Sama Mohan Das ji and others, those who have coordinated very well during the inaugural session. So my sincere thanks to each and everyone present in the meeting. Thank you very much.
Thank you, sir.
I am interrupting a little bit. Just a small statistics. We have received more than 15 countries participation and around 130 participants.
Yeah. So before moving to the vote of thanks, I request Somesh sir or Tyagi sir if there is any comments.
Okay, is Dr. Tyagi Saab there? Tyagi Saab, are you there? Okay, maybe you can join if possible. Well, it was a great pleasure to listen to all the stalwarts in the field today, including Professor Chandrashekar, the pioneer of the Doppler weather radar, I should say, in India, and also Kumar, the pioneer director, founding director of the ACARR CUSAT. Thanks very much, both of you, for giving us a very enlightening talk on the inauguration session of the Radar Meteorology Lecture Series. I'd like to say to the participants that only for today, during the inauguration session, the lecture started at 10 o'clock in the morning, Indian Standard Time. But from next lecture onwards, it will be always at 3 p.m. afternoon, Indian Standard Time. Lecture will be about 1.5 hours plus maybe lecture for 1 hour and half an hour for interaction question and answer session. So 3 to 4:30 or 5 o'clock it will go on. Also, I have seen many participants have asked whether the PowerPoints of the lecture will be available or not. Well, we do request all the speakers to provide the PowerPoints at the end of the lectures. But even if they are not available, all the lectures are available. The video recording links of all the lectures are available on the YouTube channel of the SAMA. So you can watch it anytime the lectures are over. And also it will be useful for all of you, all those of you who want to appear in the test at the end of the lecture series. So you can watch as many times as you want and then refresh your knowledge before you appear in the test at the end of the lecture series. So I think that's all from my side. Thank you very much, Dr. Avilas, for nicely conducting the lecture for today. I hope Dr. Tyagi Saab, he said that he is in Trivandrum yesterday. I don't know whether he's still there or he's able to connect or not. If he's there, I would like to request him also to say a few words or go for the next agenda in the program, that is the vote of thanks by Mohankumar.
Yeah. Now I think if there is no more comments, we can go towards the end of this today's program, the formal vote of thanks. Before going for that, I would like to thank my colleagues here who are helping us in organizing this event in a good form, like Mr. Ragesh, Srikala, Angel, Rijoy, Sharath, and all other students here. So, yeah, now the floor is open to given to Dr. Mohankumar Das for the official vote of thanks.
Okay, kindly make me co-host or share screen permission, please.
Yeah.
Okay. Okay.
I'm making, yeah.
Thank you. Thank you, Dr. Avilas, sir. Esteemed guests, distinguished speakers, and respected colleagues. As we draw to the close of this insightful and enriching session, it is my honor and privilege to extend a vote of thanks on behalf of the SAMA and ACARR and CUSAT India. First and foremost, I would like to express our deepest gratitude to Professor Dr. Someshwar Das, Secretary of the SAMA, for his warm welcome address that set the tone of this event. Your dedication to our association is truly commendable. A heartfelt thank you to Air Vice Marshal Retired Professor Dr. Udit Tyagi sir, President of SAMA, for your inspiring opening remarks. Your vision and leadership continue to guide SAMA towards a new height. Our sincere thanks to Dr. Devendra Pradhan sir, Chairman of the Advisory Panel, for your insightful address. Your wisdom and guidance are vital for our progress. We are also thankful to Dr. Fatima Akhtar, Chairperson of the Department of Meteorology at the University of Dhaka. So, and she is also a member of SAMA, for introducing today's first speaker and first lecturer. Your contribution to the field of meteorology is inspiring. A special thanks to our today's first resource person, Professor Chandrashekar sir, for his very inspiring and very important topic, which start the initiation of this today's lecture. We also extend our gratitude to Dr. Mili Ghosh Nilala, Associate Professor of Remote Sensing at BIT Mesra and live member of SAMA, for introducing our second speaker of the second lecture. Your dedication to advancing meteorology research is greatly appreciated. Thank you, Professor Dr. K. Mohankumar sir, who is the founder director of ACARR CUSAT, for the second lecture. Your pioneering work continues to inspire us all. Our sincere appreciation goes to Dr. Shwagata Paira, Treasurer of the SAMA, for moderating the question-answer session quite nicely. Your efforts ensured a lively and productive discussion. A big thank you to Dr. Abhilash Shukumar Pillai, Director of ACARR and Program Convener, for moderating the entire session. Your organizational skill and commitment have been crucial for the success of this event. Lastly, but certainly not least, I'd like to thank all the participants for their active engagement and contribution. Your presence, enthusiasms are what makes these events truly worthwhile. Once again, thank you all for making this session a grand success. We look forward to your continued support and participation in future events. With heartfelt thanks and wishes for a splendid day ahead. Thank you. Thank you very much.
Thank you.
Thank you, Dr. Mohan. And Dr. Mohankumar Das. Because today there are two Mohans, sir. So this is a confusion.
Yeah, we also thank Dr. Mohankumar in helping us for all, helping and guiding us in all these activities. Thank you very much.
Thank you. Bye.
Thank you, sir.
Thank you.
I think you will stop that live stream in the YouTube, right, Mohankumar?
It will automatically stop
So
once you.
yeah, if it is stop, I think it will be automatically live stream stop.
Then can I end the session?
Session, yeah. If you
Yeah.
end the session, it will automatically.
Yeah.
Yeah.
Thank you all. Thank you all.
Thank you.
Meet you on 1st June for the next talk, which will be at 3 p.m. IST. So,
Thank you.
thank you.
Thank you.